In this section, we will discuss statistical tests for comparing machine learning models and AutoML configurations. In the previous section, we established that generalization estimates are random variables and that a single number is not a reliable basis for drawing conclusions. Statistical testing is the formal machinery that lets us decide whether an observed difference between two configurations reflects a true effect or whether it's simply consistent with random variation. Let us first establish precisely what we are testing. Recall from the previous section that the estimated generalization risk is a random variable. It depends on the random draw of the data split and if the inducer is stochastic on the random seed of the training. When we compare two configurations A and B, we compute estimated risks A and B, both based on IID draws from the same distribution P. What we observe is not the true generalization risk of either configuration, but a noisy estimate of it. The natural quantity to focus on is therefore the difference, dj, between the two estimated risks on evaluation j, for instance, the difference in performance on fold j of a cross-validation. The goal of statistical testing is then precisely stated. Given observed differences d1 to dk, we want to decide whether the expected difference is zero, meaning any observed gap is just noise, or whether it is actually non-zero, meaning one configuration is truly better than the other in expectation. To see why this matters, consider a concrete scenario. We evaluate two configurations A and B on 10 cross-validation folds. The observed mean difference is d bar is equal to 0.02. Configuration A appears to be 2 percentage points better than B. Should we conclude that A is superior now? Well, the answer depends entirely on the variance of the individual differences. Consider two scenarios for this case, both with the same mean of 0.02. In the first scenario, every fold gives a difference close to 0.02. The effect is consistent across all 10 folds, and it is plausible that a true underlying difference is driving it. In the second scenario, the individual differences range from minus 0.15 to plus 0.19. The mean happens to be 0.02, but the result is dominated by noise. In this case, the observed gap is entirely consistent with random variation and we have no evidence for real effect. The raw mean difference is the same in both scenarios. What differs is its variance. A statistical test accounts for both, and this is precisely what makes it more informative than a simple comparison of means. Let us now introduce the formal framework. We formulate two competing hypotheses. The null hypothesis, H0, that states that the expected difference is zero. There is no true difference between the two configurations. The alternative hypothesis, H1, states that the expected difference is non-zero. That means a true difference exists. Before running any test, we fix a significance level alpha. This is the maximum probability of incorrectly rejecting H0 that we are willing to tolerate. I want to emphasize this point. Alpha must be fixed before running the test and before looking at the data. Choosing alpha after seeing the results, for example setting it to 0.06 because the p-value came out as 0.055, invalidates the entire procedure. The type 1 error guarantee only holds if alpha is committed to in advance. In practice, alpha is equal to 0.05 as the standard choice, basically. The p-value is the probability of observing a result at least as extreme as what we actually observed, under the assumption that H0 is true. If the p-value is at most alpha, we reject H0. Two important caveats. First, failing to reject H0 does not prove that the two configurations are equivalent. It only means we do not have sufficient evidence to conclude they differ. So, absence of evidence is not evidence of absence. Second, rejecting H0 only tells us that the difference exists. It does not tell us which configuration is better, nor how large the difference in any practically meaningful sense is. For that, we need effect sizes. Every hypothesis test can make two kinds of mistakes, and it is important to understand both. A type 1 error occurs when we reject H0 even though it is true. We conclude that the difference exists when in fact there is none. This is a false positive. The significance level alpha directly controls the probability of a type 1 error. By setting alpha equal to 0.05, we accept that in 5% of experiments where there is truly no difference, we will incorrectly conclude that there is one. A type 2 error is the opposite. We fail to reject H0 even though it is false. We miss a real difference. This is a false negative. The complement of the type 2 error rate is the power of the test, the probability of correctly detecting a true effect when one exists. These two error types are in tension with each other. Lowering alpha reduces the probability of type 1 errors, but it also makes the test more conservative, increasing the probability of type 2 errors. The power of a test can be increased by having more data, by reducing variance in the observed differences, or by choosing a more powerful test, but never without some cost elsewhere. This trade-off is directly relevant to our setting. When we compare AutoML configurations across a small number of datasets, power is often limited. A test may fail to detect a real difference simply because we have too few evaluation points. This is another reason why the number of datasets in a benchmark matters. The most familiar parametric test for this setting is the pair t-test. It is parametric in the sense that it makes a distributional assumption. The differences dj are assumed to be IID and normally distributed. Under this assumption, the test statistic t is the ratio of the mean difference d bar to its standard error. Under H0, this statistic follows a t-distribution with k-1 degrees of freedom, which gives us the p-value. The paired structure is important. We are not comparing two independent groups. We are comparing the performance of two configurations on the same folds. By computing fold-wise differences dj, we cancel out the variability that comes from some folds being inherently harder than others. This makes the test more powerful than an unpaired comparison. However, there is a subtle problem when applying the pair t-test to cross-validation results. The IID assumption on the dj is violated, the folds share training data and are therefore correlated. Ignoring this correlation leads to an underestimate of the variance, which in turn inflates the type 1 error. We reject the null hypothesis more often than we should. The corrected resample t-test by Nadeau and Bengio addresses this by adjusting the variance estimate to account for fold dependency. If you use the t-test on MCCV results, this corrected version is the appropriate choice. As an alternative choice, non-parametric tests do not assume a specific distribution for the differences dj, making them more robust when the normality assumption is questionable, which in practice is quite often the case, especially with small number of folds or datasets. That said, non-parametric tests still require the observations to be IID. This means they are appropriate when the dj comes from, for example, independent datasets or independent random splits, not when they come from correlated CB folds without correction. There's an important trade-off to be aware of. By making fewer assumptions, non-parametric tests are generally less powerful than their parametric counterparts. Given the same data, a non-parametric test requires a larger or more consistent effect to reject H0. Robustness comes at the cost of power. The most commonly used non-parametric pair test in our context is the Wilcoxon signed rank test. It ranks the absolute differences dj and accounts for the sign of each difference. It is more powerful than the sign test and more robust than the t-test, making it the preferred default for comparing two configurations across multiple datasets or splits. The sign test, which I just mentioned, is the simplest option. It only considers whether each difference dj is positive or negative, discarding magnitude entirely. It is extremely robust, it makes almost no assumptions, but this comes at a substantial cost and power. It should be used only when the data are so irregular that even the Wilcoxon test seems unreliable. So far, we have considered comparing exactly two configurations. However, in practice, we often want to compare many configurations simultaneously. For example, a set of AutoML systems evaluated on an entire benchmark suite. A naive approach would now be to run all pairwise Wilcoxon tests, but if we have m configurations, there are m choose 2 pairs. Each test has a probability alpha of producing a false positive, and these errors accumulate. The probability of at least one false positive across all tests is given by this formula on the slide, which grows rapidly with m. For m equals 10 and an alpha of 0.05, this is already above 90%. Running uncorrected pairwise tests in this setting almost guarantees false positives. The correct approach is to first apply an omnibus test, a single test that asks whether there is any difference among all the m configurations at all. The standard choice in our setting is the Friedman test, a non-parametric omnibus test that operates on m configurations evaluated across n datasets or splits. For each dataset, the configurations are ranked by performance. The Friedman test then checks whether the mean ranks differ across configurations more than would be expected by chance. Crucially, it makes no claim about which pair of configuration differs. It only rejects or fails to reject the global null hypothesis that all configurations perform equally. If the Friedman test rejects H0, we then proceed to post hoc pairwise comparisons with appropriate correction for multiple testing. Several correction procedures are available, and they differ in how conservative they are and what error rate they control. The simplest is the Bonferroni correction. Divide alpha by the number of tests m, so each individual test uses a threshold alpha prime equal to alpha divided by m. This controls the family-wise error rate, the probability of any false positive, but it is conservative, which means it increases the type 2 error rate. With many tests, Bonferroni may miss real effects actually. The Holm procedure is a step-down method that is uniformly more powerful than Bonferroni while controlling the same family-wise error rate. It sorts the p-values in ascending order and applies decreasing thresholds, stopping as soon as the test is not rejected. In practice, Holm should be preferred over Bonferroni whenever power matters. Finally, the Nemeni test is specifically designed as a post-hoc procedure after the Friedman test. It compares all pairs of configurations based on their mean rank differences and is convenient because it integrates naturally with critical difference diagrams, which you can also see here on this slide. However, it is also less powerful than Holm in general. The choice among these procedures depends on the number of comparisons and how conservatively you want to control errors. As a practical default, Friedman followed by Holm-corrected Wilcoxon test is a robust and reasonably powerful combination. Let me close with practical guidance on choosing and applying these tests. For comparing two configurations with paired results, for example across folds or datasets, the Wilcoxon signed rank test is the robust default. If the normality assumption is plausible and the folds are treated as approximately independent, the corrected t-test of Nadeau and Bengio is also appropriate. For more than two configurations, always begin with the Friedman omnibus test. Only proceed to pairwise post-hoc comparisons if Friedman rejects the global null. Apply multiple testing correction. Holm is a good default, and report effect sizes along p-values wherever possible. A p-value tells you whether a difference is detectable. However, an effect size tells you whether it is actually meaningful. Now the pitfalls. Using an uncorrected t-test on Monte Carlo cross-validation folds violates the IID assumption and inflates type 1 errors. Use the corrected versions instead. Fixing alpha after seeing the data invalidates the error guarantee entirely. Commit to an alpha before running anything. Interpreting p larger than alpha as a proof of equivalence is a logical error. It is simply the absence of evidence for a difference. Running many pairwise tests without correction accumulates false positives rapidly, and choosing the test after seeing the data is a form of researcher degree of freedom that undermines the validity of the entire analysis. Let us close with the key takeaways from this section. Performance differences are random variables. Statistical tests give us a principled way to decide whether observed differences are consistent with chance. The significance level, alpha, controls the type 1 error rate and must be committed to before running any test. Understanding the two error types is essential. Type 1 errors, false positives, are controlled by alpha. Type 2 errors, false negatives, are reduced by increasing the power of the test set, which requires more data, lower variance, or a more sensitive test procedure. Non-parametric tests are more robust than parametric ones, but this robustness comes at the cost of power. For two configurations, the Wilcoxon signed rank test is the robust default. For more than two, the Friedman omnibus test comes first, followed by post-hoc pairwise tests with multiple testing correction. Never run uncorrected pairwise tests across many configurations, and never fix alpha after seeing the results. Both practices undermine the validity of the entire comparison.